Right, this is problem class 1 for work, energy and power. Problem 1 has a boy on a bicycle at rest at the top of a hill 30 metres high. He coasts down the hill. We need to look at conservation of energy to find his speed at the bottom. So this means the energy is conserved from the top to the bottom. We're only talking about conservative forces here in terms of there's no friction, there's only gravity acting. So the motion is not in a straight line and the forces are not all in the same direction. It doesn't matter. We really only need to look at the loss in the potential energy being equal to the kinetic energy at the bottom. First of all, we should do a few things here. Draw a diagram to show, first of all, which way is up. I'll say upwards is positive. I like to say upwards being positive. Draw a little diagram. So you've got, could be any arbitrary shaped hill. It doesn't matter. We've got a bike at the top here with a guy sitting on it. Not my best strong suit drawing, but anyway, let's draw another bike down here with a guy sitting on it. Now, there's a vertical height between these two. So if we put his height here and the height here, well, we can set this to be arbitrarily y equals 0 here, and that would make this y equals 30 meters up the top here. So he's going to be displaced, and we'll say h equals 30 meters. Now, another few things that we have his initial velocity in this direction, v naught. What is it? It's 0 meters per second. Okay, he's at rest at the top, and we want to find his final velocity. That's what the question's asking for here. So we can use conservation of energy here. So what do we have? What do we have? Well, we have the acceleration is equal to negative g, negative 9.8 meters per second squared. We have h is 30 meters. What do we need? Well, we need the magnitude of that final velocity. That's what we need. What connects them? Connected by conservation of energy. That's our principle. It's going to connect those things together. So basically what's happening here is the kinetic energy at the bottom is going to be equal to the potential energy at the top. So we're losing potential energy to go through that height of 30 meters. That's all being converted to kinetic energy because there are no dissipative forces acting. So we can solve this now. So kinetic energy is half mv squared, and the potential energy is mgh. And our conservation of energy, of mechanical energy, equation states that the kinetic energy plus the potential energy at initially equals the kinetic energy plus the potential energy final. So that's conservation of mechanical energy. There's no losses due to friction. So the kinetic energy equation, let's write this down. Kinetic energy only contains speed. Okay, it's a scalar. That's good. Is independent of the direction. So it's just a scalar. A couple of other things. The h in mgh, mu equals mg, u equals mgh, is the vertical distance that the boy and the bike move, not the distance along the slope. So it's the vertical distance. Vertical distance, not distance along slope. Okay? Because you're only doing work against gravitational potential energy in the vertical direction, so it's not this distance along here. Okay, it's this one that we're looking for. Okay, so that's because, yeah, the delta PE, which is the work done, or delta U, let's call it, is negative work done. So only the force of gravity acting along that path does any work in that direction. So we can use our conservation of energy equation now. So by conservation of energy, we can make the statement K plus U initially equals the mechanical energy, total mechanical energy afterwards. We have two situations, the top and at the bottom. So this means, we can write this out now, we have those expressions, half mv squared, so that's the initial velocity, we'll call that v naught, plus mgh initially equals half mv final plus mgh final. And this works out pretty nicely because v equals 0, our initial velocity equals 0, that disappears. And we can arbitrarily set this value here at y equals 0 or h equals 0, that disappears as well. So what we end up with is that the initial potential energy, mgh naught, equals the final kinetic energy, mv squared final. So all of our potential energy is converted to kinetic energy. There's no losses due to the dissipative force of friction because we have ignored it in this question. So we want to solve, that's a vf squared, sorry, and also here. It's a typo that I've just managed to pick up. So the m's cancel, which is good. So we get vf squared, just by doing some algebra, vf squared equals 2gh naught. Yes. So therefore, v final, which is what we're looking for, is the square root of 2gh naught. We can throw some values into that now. Square root of 2 times 9.8. Notice I didn't put minus 9.8 because it's asking for g. Times 30, which was our initial height. So therefore, v final is 24.5 meters per second. Okay, that's excellent. So if we had friction, with friction, that would be less. So you can do that for a test for yourself. Put in some loss, some energy loss due to friction. You don't even need to go overboard and know what the coefficient of friction is. Just say I lose X number of joules of energy because of friction. Then see what your final kinetic energy will be. It would be less. So your final velocity would be less. Okay, that's the answer. Okay, so the next question says a straight luggage slide is inclined at 37 degrees to the horizontal. A suitcase of mass 10 kilograms starts sliding from rest at the top. And after 2 seconds, it's traveling at 1 meter per second. So we're basically letting the suitcase slide from the top of a ramp, and after 2 seconds, it's traveling at 1 meter per second. So this is a combination of a force diagram and some equations of motion and a few other things to solve the problem. First of all, we're asked to find the coefficient of friction between the suitcase and the slide. We have enough information, but we're going to have to use a bit of trickery. First of all, we start by drawing a force diagram. So I first of all draw my inclined plane like this, and it's at some angle theta. I like to draw in the positive directions. So this is positive x and this is positive y. It just makes solving the problem a little easier if we do this. And then I draw the force diagram. So I'm going to have the particle sitting here. Luggage is a particle at this point. Now we're going to have the force of friction acting back this way, Fk. I say Fk because it's kinetic friction acting, because the thing is actually sliding. I have a normal force acting out this way, which I'll just call N. And I have mg acting downwards. So that's our force diagram. So start by drawing that thing. Now what's going to happen is this sum of these forces is going to end up with some net force acting this way, and that's going to give some net acceleration. Okay, so that's what's going to happen. It's good to sort of draw that off to the side. Don't make it part of the diagram, but the sum of all those forces will give you a net force which will accelerate the thing in the positive direction if Fk is smaller than the horizontal component of mg. So we should draw mg, well, N and the force of friction in line with the axes, so they're quite easy, but mg is going to have a component in both directions, so let's draw that. If we draw mg downwards like this, then there's going to be some components of that perpendicular to the plane this way, and that will be mg cos theta, and there'll be a component this way, which is mg sine theta. Okay, so you're going to have a vertical and a horizontal component of mg to consider. Then what I'd like to do is draw those force diagrams in just the x and y directions. So in x, let's just draw the x one. Well, we're going to have mg sine theta going down like this. That's this guy. So mg sine theta. And you're going to have Fk acting backwards. Okay. So in the y direction, you're going to have this force diagram. So we look at them separately. You're going to have N, and then in this direction, you're going to have mg cos theta. Okay, so we need to look at those separately to solve this problem. So for question A then, so we've set up our problem with our force diagrams. We need to find, so we need mu k. How are we going to go about that? Well, we're probably going to get it from finding out the friction force, Fk, because we know that that is mu k times n. We don't know n, so we've got two unknowns in one equation, so we're going to have to do a few other things. We also know the kinematics of this problem. We also know that Vf is 1 meter per second. We know V naught, 0 meters per second. We know the time, it's 2 seconds. And we know the mass, that's 10 kilograms. So we can find out what our net acceleration then is down the plane. So we can use one of our equations of motion. It's A net equals Vf minus V naught over T. Okay, and that comes out to be basically that's it's 1 minus 0 over 2, which is a half, 0.5 meters per second squared. Okay, so that's some useful information that we're going to have to use later. Okay, so we calculated that this thing has a net acceleration down the plane of 0.5 meter per second, and we get that just from the information given to us in the problem. So that's handy. So, and that acceleration down the plane, so I'll just write this, the acceleration down the plane is equal to F net over m. Okay, so A net equals F net over m. These are vectors. Okay, so that's pretty important. So let's have a think then about our motion in the x direction. So in the x direction, so we're going to have to use both of these directions to extract two equations that contain our two unknowns for normal and for mu. So let's have a look at the force in the x direction. Well, the net force, F net, call it F net x, that's in the x direction. Looking at our force diagram in the x direction, so looking at this guy here, we can see that the net force acting on that in the x direction, mg sine theta is going to be positive, so we get mg sine theta. And then Fk is acting back the other way, so that's going to be a minus sign. So we have an equation there now that we can use, but we can also change that to contain our mu k that we're looking for, sine theta, and we can use this equation minus mu k n. That's equation 1. So we still need another equation, and we can use the other direction to get that. Okay, so let's have a look at the forces in the other direction from this diagram. Well, you can see that if this thing's not to launch off the ramp, then n must be equal in magnitude to mg cos theta, otherwise you've got some acceleration in the y direction. So in that direction, we have F net y, which equals 0, has to be 0, is equal to n minus mg cos theta. Therefore, n equals mg cos theta. That's good because that's another equation that we can solve, we can use to solve. So if we now, we've got a couple of equations there, we can just plug 2 into 1. So now if we just take this guy and put it into here, then we can start solving this thing. So let's plug 2 into 1. We get F net. So let's just say we get F net x, which equals m a net x, acceleration in the x direction, equals, so if we're just looking at equation 1 right now, equals mg sine theta minus mu k, oh, I'll just make that a bit smaller, mu k, and instead of n we just put in mg cos theta. Okay, so this is nice because the m's all cancel out here, here and here, so it doesn't matter about the mass. Okay, so they cancel out. So we get left with a net x equals g sine theta minus mu k g cos theta. Great. So we now just have to solve that for mu k, which means we just have to subtract g sine theta from both sides and then divide 3 by g cos theta. So we can rearrange this to get mu k by itself. So we get mu k equals a net x minus g sine theta all over negative g cos theta. This is awesome because now we can just plug values in. So mu k, which is what we're looking for, is equal to 0.5, which we calculated up the top in the orange box, minus 9.8 times sine 37 degrees, all divided by negative 9 cos 37 degrees. Make sure your calculator's in the right mode, guys. 0.69. That's your answer. And you might say, what are the units? Well, it's a coefficient. It doesn't have units. It's just a number, and it basically between 0 and 1 tells us, how much friction, 1 being maximum, 0 being minimum. Right, so now we need to think about what's happening with the velocity of this object as it moves down the slide. We know that the friction is going to change the total mechanical energy of the system. It's going to dump some energy out in the form of thermal energy, so we're going to have some loss through friction, which means that in reality, the potential energy at the top is not going to be equal to the kinetic energy at the bottom, as in our bicycle problem going down the hill. So we need to work that out, and we need to basically verify that the energy loss is the same as the work done by friction. So first of all, let's start off by setting up the kinematics of the problem. The final velocity we know is 1 meter per second. The initial velocity, 0 meters per second. And we know the time taken to do that is 2 seconds. So we can work out the distance then. So I'll draw the ramp here. So here's our ramp. You've got 37 degrees here. And a couple of things we need to find here. We need to find this guy, the height that it drops down, but we also need to know this. So delta x, if you like, if you know this is x like this, and y. Okay, so we need to find out how far down the ramp it's traveling, because remember that the work done is equal to the force dotted with the delta x, basically. Okay, so we need to know how much work is done as it slides through this section of friction. So we can work out what delta x is pretty easily just from using this equation, v naught plus vf divided by 2 times t. So that's going to be a half times 2, because t is 2, which is 1 meter. So the thing is moving, it slides down 1 meter down the ramp basically in that time. So that's given our displacement. Now we also need to find out the h. Well, we can find out h from trigonometry. If this angle here is 37 degrees and this is length 1, then we can easily find that h is sine 37 degrees just from trig, which is 0.602 meters. So both of those distances are important. We need to know how far it slid down, but also the vertical height from which it dropped, because we're going to have to use our conservation of energy rules to find out what's going on here. So I'm just going to write a statement. Friction is a non-conservative force. So that means it's dissipating some energy. So it changes is a non-conservative force, therefore changes the total energy. It generally does that by converting some of it into thermal energy. Okay. So therefore, instead of having, kinetic energy at the top plus the potential energy at the top, minus kinetic energy at the bottom plus the potential energy at the bottom equal to 0, so no change, then we have some change. So there's some change in energy, delta E, which is K plus U at the top minus K plus U at the bottom. So with non-dissipative forces, that would be equal to, like delta E would be 0, but we've got some well, we want to figure out if we've got any. We could test this. We can see if it adds up. If we get 0 for the answer, then we don't have any friction acting, but we know we do. So let's do this then. Let's work it out. We get half. So at the top, we've got half mv squared naught plus mgh at the top minus half mv final squared plus mgh at the bottom. Right. So that's good. This guy disappears because there's no energy at the top, no kinetic energy at the top. It's from rest. At the bottom, we arbitrarily say that there's no potential energy left. So we get mgh top minus half mvf squared. So that's our change in energy. So if we put those values in, we get 10 times 9.8 times 0.602 minus half. M is 10 times the final velocity at the bottom, which we calculated earlier. Or we know that we're given actually it's 1, and that's a squared. That comes to 54 joules. So there's an energy loss of 54 joules. There should be a minus sign in there if you do this around the right way, but we really just know that there's a difference in energy of 54 joules from the top to the bottom. So we've lost some energy somewhere. So we can see if that's equal to the work done due to the friction. So let's find work due to friction over that surface. So we can calculate that quite easily. The force due to friction is equal to mu k n. That's our kinetic friction force. We also know from the last problem that the normal force was equal to the vertical component of mg. So we can say mu k mg cos theta. Okay. And if we want to find the work then, the work done is just the force of friction dotted with delta x. So they're both in the same direction, so that makes it maximum. So we can then write the work done is mu k mg cos theta delta x. Put in some values for that, and we get 0.691, which we calculated in the last question, times 10 times 9.8 times cos 37 degrees times x delta x, which is 1. And we get a value of, lo and behold, 54 joules. So friction's dissipating 54 joules. We have a loss in energy in this system of 54 joules. So that's just really verifying that that's what's happened. Right, so C and D are asking us to think about conservation of energy and what would happen comparing the situation between a frictioned ramp and a non-frictioned ramp. So first of all, we're going to use conservation of energy to find out how fast the case will be moving the same vertical distance from rest with no friction. So would that change if the luggage slide weren't straight but were curved up and down somewhat? So let's have a think about, first of all, what would be the velocity or the kinetic energy of this thing if there were no friction? So remember, with friction, we end up at 1 meter per second. So let's have a look at it. So we can say that the kinetic energy, so this is conservation of energy, K plus U at the top equals K plus U at the bottom. That's our conservation of energy term. And because there's no friction dissipation, that statement works. So we can say half mv top squared plus mgh top equals half mv squared at the bottom plus mgh at the bottom. This is nice. We get rid of some things. That guy at the top, the kinetic energy at the top is 0. Also, if we arbitrarily set the bottom to be height 0, that disappears as well, which means we can cancel out these m's in the equation as well. So we end up with an expression that says Vf squared equals 2gh naught, ht. Therefore, Vf equals square root 2gh top. So Vf then, put some values in, square root of 2 times 9.8 times the height at the top, which we calculated before to be 0.602. That comes out to be 3.47 meters per second. That's good. It comes out to be greater than this value. And that's because there was no energy dissipated. So no kinetic energy was dissipated there by friction if we have a frictionless surface. Does that answer change if the luggage slide were not straight but curved up and down? So it wasn't like this, but it was like, this. Does it change without friction? Well, the answer doesn't change because if the slide weren't straight, because the change in gravitational potential energy and therefore the change in the kinetic energy depends only on the vertical change in height. Okay, so from this point to this point vertically, so this distance, you can see that's the same here. Okay, it's the same because it's only, so I'll write this, it's only you doing work. Okay, that's because if you think about the work being F dot D, that's F D cos theta. If you're sliding down this thing, the only other forces that are acting on this would be a normal force pushing this way, and that is always perpendicular to the direction of travel down this way. So this guy is going to go to 0. So no work done by that normal force. Okay, and it's the same here. Like this way, there's a normal force acting. This way, there's a normal force acting. It's always perpendicular to the direction that you're traveling. So there's no work being done by that. But the gravitational force, if you're moving in this direction, mg is also in that direction. So that's maximizing the work that can be done by if you look at this equation. If we add friction into the situation, however, then you have the normal force, but you also have friction acting backwards this way while you're moving this way. Okay, so the angle between them then is going to be 180 degrees. So therefore, we get work done is negative F times D. So we actually do some work by the friction force. So we're dissipating some energy. We're doing some work. There's another force doing work, and that's the friction force dissipating some energy. So it does matter with friction present. So the curves definitely affect the final speed. These ones that are you're traveling for friction for longer over this curve. So friction's acting for a lot longer. So the work done is going to be larger because of the D there. So you're going to dissipate more kinetic energy. So your final kinetic energy will be less. The mgh that you have here is going to be, more of it's going to be dissipated by this guy. So the kinetic energy here will be less, reduced. Okay guys, stay with me on this problem. It's got a bunch of algebra, but it is a pretty cool problem because we've got two bodies here that are coupled by a massless string sliding down an incline. They have different weights. The coefficient of kinetic friction is different for the two blocks, and we assume that the light block is leading. So you can see that we have the weights here, not the masses. These are weights. We also have the coefficients of friction for them. That's what we have here. So what we're trying to find is the magnitude and acceleration of the blocks. We assume that the little one is leading and pulls the, we'll see when we solve the problem. So let's write down the data that we have. So data, we have the weight of A, block A, 3.6 newtons. And we have the weight of B is 7.2 newtons. So if we want the mass of those guys, we just have to divide by 9.8. So we can do that. The mass of A is 3.6 divided by 9.8, 0.37 kgs. This could be handy later on. And the mass of B is, again, 7.2 divided by 9.8, which is 0.73 kgs. So we've got that data. We also have G equal to 9.8 meters per second squared. And we've got these other things that we mentioned over here. We have mu A and mu B. So let's call those mu A is equal to 0.10, and mu b, the coefficient of friction, 0.20. So that's our data. Now, we should draw, first of all, to solve this, we're going to draw some force diagrams. Again, break them up into their components. But we've got two bodies here, so I will draw a force diagram for both bodies. For both bodies. Okay, so we're going to have, for A, we have something that looks like this. We draw our incline. This is 30 degrees. Hopefully this doesn't get too messy. And we've got our positive directions again, y and x. Draw those in. Let's draw our force diagram then. We're going to have a frictional force acting backwards, F, and we'll call it FA. We're going to have a tension acting back this way as well. Tension. Just got to go for a few colours here so this doesn't get confusing. And we're going to have the weight acting downwards, weight A. And always, as always, the normal force going this way. Okay, and we'll call that normal force A. I've left off the vectors, the vector signs on these, but they are all vectors. It's just to make it a little bit non-confusing in the diagram. So that's A. For B, let's draw another diagram. Well, we're going to have the tension going down this way. We're going to have FB acting back this way. So the T's, these T's, I should do them the same colour. They're the same but in opposite direction, so the magnitude of those are the same. We've got the friction force acting backwards. We've got, oh, other colour. We've got the weight of B going downwards. And we've got the normal force, NB. So I've drawn my diagrams. Now, that's good. So we need to be able to come up with some equations based on these. So we've got our Newton's laws, we've got our force diagrams. We need to equate our Newton's laws back to our kinematics. So from, like the last problem, we can define these normal forces. NA is just going to be M, well, it's just going to be WB. Let's just go back and make that a little less confusing. It's going to be WA times cos theta. Okay, so that's just, we're just going to be looking at that vertical component there, because NA cancels out the vertical components. This is the same as the last problem. This is how we find the vertical component of WA, the MGA. So MAG cos theta. Okay, so we can put values into that. So we get, basically we're going to get 3.6 cos 30, which is 3.12 newtons. So we have the size of that normal force. This is useful information for later on. B is going to be just WB cos theta. We can just put the weight value in. It's easier than using the mass. WB was 7.2 cos 30, which is 6.23 newtons. So we've got some more data there that we've calculated just from looking at this force diagrams and balancing the y components. So the N component, and WA cos theta. So we've got that information there. So now we use Newton's law. So let's write this. using Newton's law, so I'll call it N2L, Newton's second law, for block A plus B. A plus B in the X and Y directions. We're going to get a couple of equations out of this when we do it. So let's look at block A. From block A we should get two equations. If we look at the X direction and the Y direction, we should get two equations. So that's going to be pretty helpful for us, but we only have a couple of unknowns, so we really don't need it. We really only need to look at it in the X direction. So let's see what happens there. So block A in the X direction, let's balance out the forces. Well, we get WA sine theta minus FB, so FA. Just make that clearer. FA. And I will leave the signs off the top of the vectors. We know they're vectors. So yeah, we're looking at balancing out the forces in this diagram here. Okay, that's what we're doing here. Yes, so we have a component that's down the plane this way, which is WA sine theta. Okay. So that's what we've got there. And that's balanced out by force of friction pushing backwards and the tension going backwards. And that's equal to Newton's second law, ma, times a, the acceleration of this block down the plane. Right. So we could work it out in the y direction too. We should do that as just a practice. We've got na minus wa cos theta equals 0. So I'll call this equation 1. This is equation 2. Let's look at block B now. In the x direction, we have WB sine theta, so this is pretty similar, WB sine theta minus FB, but in this case we've got plus T, okay, because the tension's going back this other direction. Okay, so that's an important factor, equals MBA. Now these A's are the same. They're connected. The block is connected. It's the same acceleration, so that's good. And this is equation 3. And just for some good practice, we'll do it in the y direction as well. We get NB minus WB cos theta equals 0. And we're really not going to need those two equations. But it's good practice just to follow on. So from equation 3, we can rearrange equation 3. So from 3, rearrange that equation, and we get a value, an expression for the tension, because we want to sub that back into the other equation 1. So T equals MBA minus WB sine theta plus FB. So we can sub that back into, so sub into 1. So we can take that value for tension and put it back into here. And then we get an ugly, ugly, ugly thing. It's algebra hell. So let's write it out anyway. We get WA sine theta minus FA minus, substituting in for this, we get MBA minus WB sine theta plus FB. So we've just substituted in for the tension in there. And that all equals MA times the acceleration. Okay, so those are the same. That's algebra hell. That's all right. We can solve algebra hell. We can just group some terms around the place, and we get WA sine theta minus FA minus MBA plus WB sine theta minus FB equals MAA. Just putting the symbol over the A there, so it's getting less confusing. Okay, so then we've got to do some more yucky algebra. So therefore, grouping these terms, MA plus MB equals WA sine theta minus FA plus WB sine theta minus FB. Right, so then we finally get an equation for A, because this is what we're looking for the length of A. So therefore A, if we divide through by MA plus MB, you can see just trying to get, all I've done here is just try to get the acceleration by itself, equals WA sine theta minus FA plus WB sine theta minus FB. Bear in mind, you could have done the algebra completely differently. Okay, and we divide all of that by MA plus MB. Whatever works for you with the algebra. So I'll call that equation 5. So we're almost there. We also know that, I'll write it up here. We also know that FA equals mu A NA, and FB equals mu B NB, which we know from calculating up at the top here. We calculated those guys, and we were given these. So we can work out what those are. So plugging into those expressions, I get some values for, so FA equals 0.31 newtons by plugging it into that expression, and FB is equal to 1.25 newtons. Okay, so that's some more data that we've calculated. This is definitely not an exam question. This would be a narcissistic, horrible thing for me to do in the exam, so don't worry too much about that. The acceleration then, plugging everything back into this horrible looking thing, equation 5, is, well, I won't write the numbers in. You can do that for yourself. We've got all of those things. We've got WA, we've got theta, we've got FA now, we've got WB, we've got FB, we've got MA and MB, and the answer comes out to be 3.5 meters per second squared. Okay. So that's the answer to the acceleration. Now we have to go back and plug it back into one of our equations to find the tension. So we need to do that. So in the last problem, we came up with an equation that looks like this for the tension. So we've got everything we need to plug back into that now. We've worked out that acceleration, which we had two unknowns, acceleration and tension. So we worked out the acceleration. We can go back and find the tension. We know the mass of the second block. It's 7.73 kilograms. Acceleration was 3.5 meters per second squared. The weight of the second block was 7.2 newtons. The angle sine 30, and the FB we calculated also in the last problem to be 1.25, which gives us a tension of that, 0.205 newtons.